So thank you all for coming. I'm Ed Kent. This is my colleague, Paul Doran.
Hi.
And we're here today to talk to you about continuous deployment of machine learning models. Exciting. So firstly, just a bit about us and where we're from. We're from a company called AutoTrader, who, if you're from the UK, you may well have heard of us. If you're not from the UK, you probably won't have done. But we are the UK's largest online digital automotive marketplace. So as a company, what we do is connect buyers and sellers of new and used vehicles. So we're primarily known for our used classified car sales, but we do all types of vehicle, new and used. So if you were to go to our homepage today, you can do a search, you can type in your location, what sort of car you're looking for, and you'll get a results page that looks something like this. And as a company, we've been doing this in one way or another for actually quite a long time. Our launch sort of predates digital by quite a long way. We were first launched as a paper-based magazine in 1977, originally called the Thames Valley Trader. And we published this magazine both in the London area and then eventually expanding nationally for quite a number of years, until 1996, when we first dipped our toe into the digital kind of water, and we launched our first iteration of the website, autotrader.co.uk. Just for context, 1996 was 2 years before Google launched. So obviously the landscape was very different in those days. And even then, we had a website. The bulk of our revenue came from the print operation. And that remained until actually quite recently, 2007, was the first year when our digital operation first kind of matched the print operation in terms of revenue. At that point, it was clear to us that the future was in digital. And in 2013, we killed the print business and became a fully digital business. And we operate in both the UK and Ireland. So hopefully that just sets a bit of context as to who we are and what we do. In terms of what we offer for our customers, like I said, we're primarily known for our new and used car search listings, but we also offer a number of other tools to help people find their ideal car, including tools for searching by monthly budget. We offer reviews for both vehicles and dealers themselves. We offer tools for consumers to perform checks on the vehicle they're looking to buy. We provide guide valuations and indicator flags to help consumers get a feel for what they're buying. Is it going to be a good deal or not? Or then maybe they're going to get ripped off. And we allow people to sell their vehicle privately as well. And those valuation and price indicator products are, for me, most interesting because they're data-driven, and I'll talk a little bit more about those in a bit. What you probably won't know us for, though, is the services that we offer to our retailers as well. So we help them advertise their car with our classified listing platform. We also provide a number of other tools that they can use to help manage their stock, buy stock in at the right price, etc., including forecourt management tools and valuations. So again, those tools are driven by the vast amount of data that we collect and the products that we build from that data. Just some stats about the scale at which we operate. We're currently ranked as the 16th biggest website in the UK. What that means is we get, on a monthly basis, around about 55 million cross-platform visits. On the site at any one time, we have approximately 450,000 plus cars listed. And the stat I like most on that slide is, in terms of automotive searches at least, we get four times as many as Google. So hopefully that sort of sets the scene, the sort of scale at which we operate and the type of data that we can collect, be it from event tracking, clicks on the site, interactions, searches, through to data about the type of stock that we advertise. So just to talk a little bit more about data at AutoTrader and how we've been moving forward with that recently. This is the AutoTrader data platform. So at the heart of this is a data lake. Hopefully you all know what a data lake is. This is just a vast, immutable store of data that we host on Amazon S3. In that data lake, we have data stored in its rawest form, including both JSON and Avro data, through to more refined data sets in formats like Parquet. That data is at a scale at the moment. We've got around 200 terabytes, and it's being ingested into the lake at a rate of about 250 gigabytes a day. So we're not as big as some organizations in terms of the volume of data we collect, but that's still definitely big data. So going into that data lake, we ingest data from operational databases across the company. So we've got Oracle, Microsoft SQL Server, MongoDB, for example, and all that data is ingested into the lake periodically, as well as streaming data from our streaming-based platform, Kafka. Orchestrating that ingestion and a bunch of the other computation that happens on the lake is our scheduling tool, Apache Airflow. I'll talk a bit more about that in a minute, but that lets us construct directed acyclic graphs of the sorts of tasks that we want to schedule on a periodic basis, and it's very powerful. DAGs themselves are written in Python, so they're written as code. So this lets us do cool stuff like write tests about the DAGs themselves, which is quite good. So sitting on top of that data lake is our compute platform. For that, we're primarily using Apache Spark. So that's a big data distributed computing platform that can read off a variety of data sources, including HDFS, and it can also read directly from S3. So for Spark, we're using a managed solution provided by Amazon called EMR, Elastic MapReduce. That takes away the pain of having to manage a Spark cluster, which if you've ever had to try and do, I'd not recommend. And because it's cloud-based, we can spin up clusters on demand and terminate them when they're no longer needed. We also have a tool called Athena, which is another Amazon product, which lets us access the data in that lake through a SQL-like interface. So what's that data actually for? So we use it to do advanced analytics. So we've got data analysts and data scientists working at the company, and they use tools like Looker, which is our business intelligence tool. Lets them produce dashboards, visualizations and things, and share them around the business. And Databricks, which is an interactive notebooking tool primarily used by our data scientists. Databricks in particular is really powerful. You can write code in Scala, in Python, in R, directly interact with Apache Spark, and do really cool stuff with that data. That cool stuff includes building our data-driven products. So I talked about valuations earlier. We also have products that do things like supply and demand forecasting, recommendations, and calculating search relevance. That's all computed in the lake using our Apache Spark compute layer.
Okay, so today we're going to talk about continuous deployment for machine learning models. So we just wanted to briefly cover what we mean by continuous deployment at AutoTrader, and briefly cover the delivery platform we have at AutoTrader that allows us to do continuous deployment. So a lot of people will be familiar with the typical continuous delivery pipeline, where you have unit tests, integration tests, you deploy to test stage in, you run some acceptance tests. All those steps will be executed automatically, but there'll be a manual trigger to deploy to production, so there'll still be a human intervention. You do the deploy to production, and then you do your post-deploy tests. For continuous deployment, there's one difference, and it's very important. The deployment to production is now automated. So you still do your unit tests, you still do your integration tests, you still deploy to your staging environment, you still run your acceptance tests, but you have that much confidence in your acceptance tests now. You don't want to delay delivering the latest version to production, so you immediately deploy to production and run the post-deployment tests. So if you've read the latest ThoughtWorks technology radar, they've called out a technique called continuous delivery for machine learning. It's in the trial phase. And the articulation in the radar is really good. So they claim it fixes two main problems: the long cycle time between training and deployment, and production models being used on stale data. So this is a problem we have in our business. If we're delivering machine learning insight to retailers that are paying for a product, we want it to be as up-to-date and as accurate as possible. So the main point of the continuous delivery for machine learning is that you apply traditional software continuous delivery practices to machine learning, but now instead of not only just worrying about versioning your software, you also need to version your data and your model as well. And the whole point of this is that we want to deploy the model as quickly as possible, as frequently as possible, so we're continuously delivering the value. So one of the key things that allows us to do this at AutoTrader is we have a delivery platform. So the delivery platform has three main components. We use GoCD for the release automation, so the pipelines of automated tests you saw before, they will be running GoCD. We use Docker as our containerization tool, and then we have Kubernetes as our container orchestration. So we're running hundreds of microservices, so the container orchestration is really important for us. So just a brief example of what a Docker file might look like for one of the machine learning models we're talking about. So you have some basic commands to install some dependencies. You download some stuff from AWS. you build and run your application. So this is the artifact that's going to be deployed to Kubernetes. So Kubernetes is an open source system for automating deployment, scaling, and management of containerized applications. It's essentially a runtime for Docker containers. It has lots of inbuilt features which are really useful, such as automatic load balancing and scaling, self-healing, health checks and monitoring, rolling deployments. It's developed by Google, but it's open source. And at AutoTrader, we use the managed service that's offered by Google in GCP. So by using Kubernetes, we can do continuous deployment because it supports rolling deployments. So we'll just briefly cover what a rolling deployment means for Kubernetes. So the unit of work in Kubernetes is what's called a pod. So it's a group of one or more containers that has shared network and storage. And it essentially models an application-specific logical host. So here we have an example of a container two pods deploy behind a single load balancer that represent a single web service. If we build and deploy a new version of our web service, Kubernetes will deploy the pod. It doesn't get put behind the load balancer yet. It has to pass a set of post-deployment smoke tests. Once those smoke tests are passed, the new version of the pod rolls behind the load balancer and one drops out. And it carries on like that until you've fully deployed the new version of the web service. So what does this mean for doing continuous deployment for machine learning models? So one of the key decisions we had to make, that if we wanted to take advantage of the delivery platform that exists at AutoTrader, we had to treat our machine learning models as web services. So a trained model is run as a web service, and it serves predictions. So the basic pattern that we're going to go through today is shown on this slide. We'll go through two examples. So there's two components to the pattern. So the top row there is the machine learning side. So you generate some training data, train a model, and you save the trained model. And the trained model is saved to S3, and then you make a Git commit. So obviously by making a Git commit and push into a repo, we can trigger a web service deployment, which is what the bottom pipeline does. So because we've made a commit to Git, we can now build our service. So it loads the trained model, runs some unit tests and integration tests, builds the container, and publishes the container. The publishing of the container triggers a deployment to Kubernetes. So we deploy to the pre-prod environment, run some acceptance tests. If they pass, we automatically deploy to production, and then we run the acceptance test again to make sure everything is OK. So we're going to cover two examples. Ed's going to talk next about days to sell, which is a retailer-facing example, and then I'm going to talk about consumer recommendations. So over to Ed.
Thanks. So the first example of a machine learning model that we used this pattern on was a model that we developed called days to sell. So this is a metric that we provide to our retailers as part of a tool that they can use to manage their forecourt. And it's literally a prediction of how many days we think a particular used car is going to sell based on how well it's priced to the market. And it probably stands to reason that if you price a vehicle too expensive, it's going to take longer to sell on average. If you price it really cheap, you're going to sell it very quickly on average. And for a retailer, it's really important to balance that. Obviously, the faster they turn over their vehicles, the more profit they're going to make in the long term, but equally, they don't want to make too little profit on a single vehicle. So here's an example of one of the retailer-facing tools that we provide to retailers. This is a tool called Retail Accelerator, and it helps them source stock at the correct price and then price it to market effectively. So typically what a retailer would do is enter a few basic details about a car, so license plate and its mileage. We do an automated lookup to figure out exactly what vehicle it is and how old it is, and then we provide some insight in the form of valuations and metrics. So you can see in this example, we've done the lookup and we've determined that its market value today at retail is £5,780, and then below we display some metrics that might also be useful. And in this example, one of those is average days to sell, 36 days. So what the retailer can then do is then adjust their pricing based on that valuation, and they can see, based on this model, how that average days to sell will change. So before we go into detail on how we deployed this, I just want to call out one quite important difference between deploying a model and developing the model initially. So I've called the two phases in which a model lives, the discovery phase and the production phase. So the discovery phase is where our data scientists work. This is where they do experiments with data. They make a lot of trial and errors. They work in an interactive environment. And it's more akin to running scientific experiments than kind of any sort of formal engineering effort. So in the discovery phase, this is where they use Databricks interactive notebooks. Those notebooks let them do very quick iterations. They get very fast feedback on the model, so they can make a change. They can rerun a cell, instantly get result back. And that's really powerful. It makes developing that model much, much easier. One important difference with the notebooking environment, though, is that while you can generate predictions for a model in the context of that notebook, it's very difficult to then make those predictions available outside that immediate notebook. And that's where the production phase comes in. So this is where we run automated model training and automatically then deploy that trained model. In the production phase, the feedback cycle is much slower. So it's not suitable for running kind of quick experiments to try and determine how best you might construct this model to begin with. But what it does give you is fully automated testing. So that's unit tests and then tests around the integrity of the data that go into the model. And that lets us fully automate the deployment using the pattern that Paul demonstrated earlier. Because of that level of testing, it's much more resilient to the discovery phase. And most importantly, because we make the model available as a web service, it lets us provide online low-latency predictions. So for the data to cell model, the discovery phase looked something like this. So our data scientists were working in an interactive notebook, and they developed what's called a Spark ML pipeline. Very briefly, what this lets you do is chain together two types of things, transformers and estimators together. Now, transformers, very, very simply, take a frame of data, sort of like a table of data, and return another data frame. Estimators, on the other hand, take a data frame, provide a fit method, and then return a transformer, so then something that takes a data frame and returns a data frame. In practice, what that lets us do is define a pipeline of transformers and estimators, run fit on it with some training data to get a fitted pipeline model. That pipeline model provides a method called transform, into which you feed some data, and that generates the predictions. So if that's a little bit abstract, here's what it looked like for the data to cell example. So first of all, we had to generate some training data, and based on the work our data scientists did, we determined that the things that had to go into this training data were things like historic advert data, so what vehicles were advertised on the site at what time, at what price, some detail about our vehicle taxonomy. So that's things like the makes, models, fuel type, number of doors, engine size, etc., that we know about all the vehicles that are on the market in the UK today. We loaded in some valuations, so our opinion on how well priced those vehicles were relative to the market, along with some geographic data around where those vehicles were located in the country. So having generated that pipeline, that training data, our data scientists constructed this pipeline model. That's as much detail as I can go into that. Top secret, proprietary, etc. But that pipeline has this fit method. So we fit that pipeline to our training data to get the fitted pipeline model that then exposes this transform method. So with that transform method, we then feed in information about the vehicle that we want to get predictions for. So its make, its model, its age, etc., its valuation, and where in the country it's located. Call transform on it, and out at the end pops our data to cell prediction. So our data scientists worked iteratively in the interactive notebooking environment to develop this kind of optimal set of transformers, estimators, and hyperparameters around those estimators. Once they'd done so, it was then up to us to productionize that model with automated deployment and training. So the first phase of that was to take that Databricks notebook and effectively recode it as a standalone, self-contained jar. Effectively, what that meant was that we take a notebook, and at the end of it, we get a deployable Java artifact. The benefits of doing that, well, there's a number of them. Firstly, we were able to write automated tests in the form of both unit tests and integration tests. So for something that we're deploying through continuous deployment, that's really important. So that was good. Secondly, it allows us to integrate with Airflow, our scheduler. So I talked about that earlier. So in the context of the wider data platform, that's really important because it means we can schedule this as a Spark job to run on our Spark cluster, just as we would any other production Spark workload. And then finally, perhaps it's not something you might have thought of, but for us this was important. It gave us an extra stage of code review. So our data scientists worked to develop this model. They then handed the notebooks over to the data engineering team. So for us, we might have been tempted to sort of think of this model as a bit of a black box, something you feed in some training data, out the end you get predictions. But in having to understand how that model worked, to recode it as a standalone Spark job, knowledge about kind of low-level workings of that model was transferred across the wider team. So we've got a standalone Spark job triggered by Airflow, our scheduler. And I mentioned Airflow runs on this concept of directed acyclic graphs. Here's an example of how it looked for days to sell. So we've got 3 Spark jobs there. The first one is generate the training data. But we can't do that until the various data sets that training data depends on are all in place. So typically in the data lake, we've got lots of ingestion happening, and a lot of our data sets are snapshot-based, so they're loaded into the lake periodically, typically once per day. So we don't want to run retraining of this model until the training data is generated, and we don't want to generate that training data until the dependent data sets are all in place. So with Airflow DAGs, we can capture those dependencies quite nicely and put sensors on those dependent data sets so that the Spark job to generate that training data won't run until everything's in place. Once the training data is in place, we then ran some integrity checks on that data. So that was really important just to make sure that things like row counts were as we expected, looking at standard deviation of particular values in that data versus previous days equivalent of that training data, which again helps give confidence that if we were to run this thing in an automated fashion without any manual intervention, that we can be confident that what comes out the end is trustworthy. Finally, if those integrity checks pass, the final Spark job trains that ML pipeline and finally runs some final tests on the trained model, just as a final step of verification. Once that's run, we write the trained model out to S3 using Spark's internal ML pipeline format. So having trained the model, we had to deploy it. So just for some context, at AutoTrader, we've got a number of data-driven products, including our vehicle valuations. Those are served out through a metric aggregator web service. So that's a single point in which something like a front-end app, so something like the forecourt management tool that I showed earlier would call. We've also got relationships with various third parties, so insurance companies, vehicle auction companies, etc., can call this API. And then finally, we've got a stream processor, which we use to integrate these various data-driven metrics into our search index. Each of those calls this metric aggregator service with some basic information about the vehicle. So it's make, model, age, mileage, and location. And then that metric aggregator service calls out to a number of microservices to get vehicle valuations, information about the vehicle taxonomy, price indicator flag, so how well priced it is. And we felt, given that we already had this, it was in this context that we should serve out our data to sell metric as well. So we've got front-end apps calling this service. Front-end apps, typically, the user likes to get a response fairly quickly, so it's important that this service is relatively low latency. Same with our third-party APIs. And then finally, our stream processor is used to process millions of messages every single day to attach these metrics to our search index. So in order to get that kind of throughput, again, low latency is really important. So our first attempt to write a web service to serve out this model looked something like this. So Apache Spark is primarily known for being a distributed computing engine, but it can also run in a mode called local mode. So effectively, rather than running across a large cluster, it runs in a single JVM, and it can be used on a single node of a cluster, for example. So Apache Spark is written in Scala. We wrote our web service also in Scala using Spring Boot. Within that web service, we created a local Spark context, loaded in that fitted pipeline model from S3. That exposes this transform method, which can then be used to attach predictions to incoming requests and serve out a response. And that worked, technically. It did what it was supposed to in the sense that it was successfully able to attach the correct predictions to requests and serve them out. But it was really, really slow. So we sort of typically saw response times in the order of hundreds, if not thousands of milliseconds, which for a front-end app or something needing to get high throughput is just not acceptable. It also completely choked under concurrency. So it was quite clear to us that this was not going to be a suitable way forward. And by the way, this is not what Spark is designed for. We were kind of abusing it, so it's not a fault of Spark itself. But we did need to rethink our approach. So we did a bit of searching and came across a library called mleap. Mleap is designed to solve exactly the problem we were having. It's designed to serve out Spark ML pipelines in a low-latency, highly concurrent way. So mleap provides a runtime that also provides a transform method exactly the same as Spark. The only caveat is that you have to take your Spark ML pipeline, which is in Spark's internal Spark's internal file format, and convert it to mleap's own internal file format before you can use it. But with that, we were able to get our response times down into the tens of milliseconds, which was more than acceptable enough for this particular example. Nothing about that, so everything else about that web service stayed the same. Because the transform method exposes itself in exactly the same way, it was quite an easy replacement to make. So this was our Airflow DAG. We had 3 Spark jobs, the final one being train the ML pipeline and just run some tests. So we added a final task onto that DAG. So once the ML pipeline has been trained, a final task just to convert that to mleap's format and then save it out to S3 again. And actually, one thing I want to point out is that when I say write it out to S3, every time we run this, it's typically once per day. We're versioning that model by including the date that the Airflow DAG runs in the path on S3, so that each day we get a new model written to S3 with a different date in its path. So because the date is in the path, what we can then do, as Paul mentioned earlier, is trigger a Git commit. So we've got the Git repository that holds the web service. In that is just a piece of config that is the path on S3 where the latest version of that model lives. So we make an automated commit to Git to say, hey, the latest version is now over here. Do your thing. And that triggers an automated deployment, which deploys just as any other web service AutoTrader would. So first of all, we have to build the application. So in our case, that involves sucking down the latest version of that model from S3, building the application. It's a Spring Boot app built with Gradle, and then run some automated tests, just as we would any other application. I say just as we would. So one final kind of important thing around testing I'd like to point out is how we test a web service with a dynamically retraining model. So unit tests, in this example, worked exactly the same as any other web service. You test small, isolated pieces of your code, and you give them known input, expected behavior, or expected output, etc. And that was fine. Integration tests were a bit harder, though. So typically, we would run integration tests on a web service by feeding real requests to a real instance of that web service and checking the response is equal to some expected value for that response. In this example, though, because we're retraining the model so frequently, it's really difficult to know if the number that's coming out of the web service is actually what we would expect it to be. We might know what it was serving out yesterday, but if we rerun it today with the most recent version of that trained model, it's difficult to know. So we got around that by, at the time of training the model, we also generated a set of known inputs, outputs for that model, so that when it came to running the integration tests, we could load that set of known input-output data and use that to run the integration tests. So assuming all those integration tests have passed, the final stage is to publish the container to our container registry, which triggers a Kubernetes deployment, just as it would any other web service at the AutoTrader delivery platform. So that was our days to sell model. Just to summarize the kind of flow that I went through there, We had a discovery phase. That's when our data scientists worked in Databricks notebooks to develop this Spark ML pipeline. So that's this chain of transformers and estimators. Once the data scientists had determined kind of what that pipeline should look like and what the training data should be to go into that pipeline, the data engineering team then took that and rewrote it as a standalone Spark job. That Spark job is triggered by Airflow, our scheduler. It runs once a day. First of all, it produces some training data. It then uses that training data to refit the Spark ML pipeline. Assuming that the automated tests that run at the same time as that all pass, we then convert that ML pipeline to the mleap format and trigger a Git commit on our web service. The web service builds by loading in the most recent version of that mleap model, wrapping it in a Spring Boot web service, and then containerizing it and deploying it using Kubernetes. So that's one example. Paul's going to run you through another example now using that same pattern on consumer recommendations.
So this is after we'd done the data sell model, we wanted to try the pattern out elsewhere. So a classic example of that is consumer recommendations, which was a problem that had not been tackled at AutoTrader previously. So again, we have the same two-step discovery production phase process. Obviously, we could take the learnings from the data sell model forward into the discovery phase for recommendations. So we'd already proven out a way of getting a Spark ML pipeline through to live by a continuous deployment. So that felt like a sensible place to start. So after doing some quick research, you discover that Spark ML actually has some suitable algorithms in it for doing consumer recommendations. There's one called alternating least squares, or ALS. If you Google it, you'll see companies like Spotify have successfully used it for doing consumer recommendations. So that felt like a really good place to start. So also because we are building consumer recommendations, we can take advantage of being able to run A/B tests on the actual the public-facing website. So we put a recommended strip on the homepage that looks something like this. So based on your previous search history on AutoTrader, we'll recommend 4 cars that we think are relevant to you. So one thing we actually discovered during the discovery phase and running the A/B tests was that the ALS model didn't perform particularly well for AutoTrader due to some quirks we think in our domain. So the data scientists decided that we should write our own recommendations algorithm. And this is what we productionized. So we'll just quickly cover the automated model training. So again, we have the similar data sets to what Ed was talking about for data to sell. We have the vehicle taxonomy and we have advert data. So one of the problems with the alternating least squares, it was actually recommending vehicles that we didn't have adverts on the site for, which obviously not particularly useful. So we introduced the concept of a group. So a group is a vehicle that exists in our taxonomy that is actually advertised on the website. So you can see here there's 4 examples. So the Citroen C3 is advertised, so it becomes a group. And you can see here there's 2 forward focuses. So sometimes manufacturers have overrunning production years for similar models, so we have to take account of things like that as well. So again, the forward focus is advertised, so we want to include that as a group. The DeLorean, unfortunately, is not advertised on AutoTrader, so it's not a group that we can recommend. So once we've computed the groups that we wish to make recommendations from, we can take advantage of the really rich session data we get from the consumer website. So obviously having 55 million unique visits a month gives us an amazing data set to pull these, to use for these machine learning models. So we compute co-occurrences of groups in sessions. So you can see 3 example sessions here. So you can see in session 1 that the Ford Focus and the Volkswagen Golf were searched for in the same session. In session 2, the Ford Focus was searched for with the Volkswagen Polo. And then in session 3, the Ford Focus was appeared in the same searches as with the Volkswagen Golf. Sorry. So we can use those that session data to compute co-occurrences. So based on this example, we can say that the Ford Focus co-occurs with the Volkswagen Golf twice, and the Ford Focus co-occurs with the Volkswagen Polo once. So using this co-occurrence data, we can compute a similarity metric. So we're quite fortunate for this application that the prediction space is small enough that we can actually compute all possible predictions for the model. So we end up with some output like this. So for a Ford Focus, we might recommend a Volkswagen Golf or a Volkswagen Polo. So we'd also observe during the A/B testing that having duplicate manufacturers in the recommended strip reduces performance. So we had a simple business rule to remove duplicate manufacturers and just keep the most similar. So in this case, we'd drop the Polo, but keep the Golf. So now we can do the automated model deployment. So again, we have a similar pipeline to what we've seen previously. We have some training data. We compute the groups. We compute the co-occurrences. We compute the recommendations. And then we update the model location. And because we update the model location, which contains the version, we can run a web service deployment. So we get the recommendations from S3. We build the application. We run the automated tests. If they pass, we can publish to a container registry, which triggers the Kubernetes deployment. So again, just the brief summary. So again, we use Databricks as a discovery tool, and then the production workflow. So again, we've got an Airflow DAG that's scheduled for running the machine learning training. That would compute the Spark model. So the difference here from the previous example you've seen is we are not using MLeap because we're not using Spark ML. So we don't need to actually serialize a pipeline. We can just write out all the data we need for the model. That location is updated in Git, which triggers the deployment. Again, we've got a Spring Boot web service that loads the data. We can containerize it and deploy it to Kubernetes. So brief summary. So hopefully through those two examples, you can see where we've applied this pattern. We believe that whilst the pattern works for the technologies and tools we've talked about, it should also be applicable to different technologies and tools that you may be using in your own workplaces. So again, for us to be able to do continuous deployment at AutoTrader, we had to treat our machine learning models as web services. We have requirements around doing low latency, high throughput predictions. Web services are good at those kinds of things. So the pattern, again, is composed of two parts. We generate the training data, we train a model, we save the trained model, and we make a Git commit that contains all the version information the web service needs. Because we're making a Git commit, we trigger a deployment. The deployment would build the service, so we would load the trained model, run our automated unit tests and integration tests, build the container, publish the container. By publishing the container, we trigger a deployment to our pre-production environment. And because we've invested the effort to have the confidence in our acceptance tests and integration tests that we run around deployments, we can also automatically trigger our deployment to production. So that's it. So we have an engineering blog at AutoTrader. There's quite a few articles on there from the data engineering team. The data engineering team are currently hiring developers. So if you're interested in working at AutoTrader, please grab me and Ed after if you want to find out what life's like at AutoTrader as a developer. There's a few of our colleagues here as well from different product teams. They'll be able to answer your questions as well. And if you have any questions, feel free to tweet us. Thank you very much. Any questions?
You were first.
In which phase you make the cross-validations of models?
So the question is, in which phase do we make cross-validations of models? I'm not sure I understand the question, actually. Could you elaborate?
Like the test, when you test the models with the test data, separated from training data. In which phase?
So it's in both, really. So when the data scientists are developing... Sorry?
Repeat the question.
Sorry, yeah, the question is, in which phase are we running these tests on the model? And it is in both. So when the data scientists are running in these notebooks, obviously they're trying to optimize the model, and they're running and rerunning various tests to get output metrics on how well that model is performing. When it comes to the production phase, we've got some basic criteria on, for example, coverage or root mean squared error from the model, for example. It's got to meet some minimum criteria for us to determine it's been a successful train of that model. So it's in both phases.
Those kind of model metrics are also saved to S3, so the data scientists have Looker dashboards that allow them to track those things over time.
Yeah.
So your nightly process to retrain it, how long does that nightly process take? And do you see, I mean, you're adding, was it 55 gigs a night of data to your data lake? Is that time increasing or is it pretty flat?
So the question is, how long does that retraining process take? It's typically of the order of tens of minutes. It's not bad at all. We probably could optimize it further, but actually for our use case, it's more than performant enough. In terms of adding more data into the lake, so we're actually ingesting around about 250 gigabytes a day, which is obviously quite a lot. As that data increases, actually we're looking back at a fairly static window of time. So for these models, we only want to serve out data that's considered relevant. So I can't remember the exact statistics, but we're looking back maybe a month or two, and that rolling month window doesn't actually change. So in terms of performance of the model, that's not an issue.
Yeah, and it's similar for recommendations. So we only look back 7 days because we know from the history we've got there's quite, you get seasonal trends in make model searches or whether a car appears on an advert or a popular television show. So trying to account for those things as well.
Okay.
Want you? Okay. So I'm just curious how much overlap exists between the data scientists and the rest of the engineering for moving a model from a notebook down to an application, a Kubernetes cluster.
Yeah, so it's a huge amount of overlap, actually. So our data scientists and data engineering team sit together. So kind of from an organizational perspective, that really helps. We talk to each other daily. And when it comes to productionizing it, it is a team effort. So if we have questions, we can go back to the data scientists. They can clarify things. They can give input. They can look over our code, review it, make sure that we're doing things correctly.
Did you have to go through any training with Did you have to go through any training with a data scientist to learn about the rest of the system?
In our case, no. Our data scientists were pretty on the ball. But I can imagine that would be something that we might have had to do.
I think the challenge we've had culturally around data science and data engineering is actually getting data engineering involved early enough in the discovery phase. So time's not wasted by data scientists trying to optimize a process that we already know how to optimize.
I'm just curious because it might be my ignorance in this area, but the integration tests. How often do you have failures at that level? I mean, how presumably in the discovery phase of the model creation, there's a certain amount of tests. There's a certain amount of testing done, or is that to what extent do you catch errors, and what kind of errors?
So actually, I'm trying to recall. I don't actually remember an instance of these tests failing. Obviously, when the model's going in discovery, we find issues in terms of maybe there's some edge cases that the model doesn't perform well on that we have to exclude, or maybe there's I don't know, some fundamental change in the input data that means where the model previously worked, it no longer works. But we were actually pretty comprehensive in our testing strategy.
Yeah, I mean, the usual failure is around things we can't control. So like we're ingesting from other production databases, so if they're having an issue, then all our training is delayed as well and things like that. That's more likely.
Any more questions?
Thank you, John. It's like following on 2 questions previously. The first is when you retraining when you're training on the data, are you just reusing a pre-trained model like from the previous day and using the new day of data, or are you retraining from scratch the model?
So for recommendations, we retrain from scratch.
Same with data cell, yeah.
Okay, always on the past week or the past month. Okay.
No.
The pipeline you mentioned in the discovery phase, I guess it's the steps to merge the data sets, clean the data, transform them, and train the models. How much work do you have to convert that for the production phase? Because pretty much you could just like import the notebook and run it. What you have to do to update it?
So I think that's probably going to be dependent on the use case. So there might be other refined data sets that we can already reuse from the data lake that the data scientist wasn't aware of previously. But like sometimes around the refinement we had to do with the session data was quite involved.
Okay, so anyway, it would be pretty much his work, but you refine together. Okay.
Yeah.
Question is related to Airflow. we are implementing it, using it. The question is, are you happy with it? What is how long have you been using it? And if you started today, knowing what you know now, if you would still apply Airflow or other solutions?
So I'm not going to say we're completely happy with it. It's definitely a powerful tool, and it's let us do everything we wanted to do. I think we've definitely had some pain points. Perhaps one thing is how to construct a DAG and what the scope of that DAG should be. So the way that we've approached it is that each DAG has a kind of fairly well-defined task. So in the example of the data to cell model, the DAG is responsible solely for producing the training data and then saving the trained version of that model. Everything that it depends on exists in some other DAG. So chaining those dependencies together is quite difficult. So another approach would be to have one kind of super DAG, depending on the schedule that you need to run. So if you've got a set of tasks that run daily, you could have one big DAG, and then everything is contained in that single DAG. So one big issue that we've got actually is trying to figure out what data sets are used where. So we have no kind of central data catalog. We've got an Excel sheet that we use to try and keep track of what data sets are being used where. But if, for example, we want to up the version of a data set or make a breaking schema change to that, actually trying to trace back and figure out what data sets are being loaded from where is quite difficult.
So we did start off by trying to build our own scheduling system. I would definitely recommend against that. And we're now running Airflow in Kubernetes. We probably did that a bit too soon and had some problems, but we've got it working fine now as well, so it's good.
Thanks.
Any more questions?
Thank you very much. Thank you very much. Oh.
One more.
Oh.
How successful do you predict? Your prediction dates, how much does it vary?
Are we allowed to say?
I don't know if we're allowed to say that, no. It's very successful. Thank you.
So there are competitors in the space, so revealing stuff like that's commercially sensitive.
So about productionization of the model, it seems a quite heavy task involving both data scientists and engineers, which probably can be quite error-prone. So how often does that actually happens compared to the daily retraining of the model using the latest data?
So, I mean, the daily retraining happens every single day.
Yeah, but actually having a new model going from that notebook to production, is that also daily?
So it's relatively rarely, especially kind of compared to once a day for a retrain. We've got
so there's
a couple of examples.
There's like legacy machine learning things that we have around valuations that have not yet been moved to the data platform. There's 3 metrics in the dealer products that went through this similar workflow, and there's now 2 that are consumer facing as well, so recommendations, and one other one around search relevant for some of the in-advertising products we have on the search results.
Mm-hmm. It's worth pointing out we have made some refinements to the model over time, and in those cases the data scientists themselves have raised pull requests on the model that we can then evaluate and merge.
I think the time taken depends on the domain as well. So like when we're doing retailer-facing things, because we're going to charge money for those things, more time's being given to those things. When we did recommendations, I think it was probably 3 weeks from having the idea to actually having it productionized and on the homepage.
Go on. One last quick question. No.
Awesome. Thank you very much.
Thank you.